Okay, let's dive into this. Welcome to today's explainer. We're going to unlock the elegant, kind of beautiful simplicity behind complex engineering systems. We're talking about mastering the structural logic of bond graph junctions. If you've ever stared at a massive multi-domain engineering model and just thought, how on earth do we predict where the energy is actually going to go? Well, you are in the exact right place. Bond graphs are absolutely crucial because they act as this universal language. They let us map out electrical, mechanical, and hydraulic systems using the exact same framework. So instead of getting totally bogged down in completely different equations for a motor, and then a battery, and then a hydraulic pump, we can just unify them. And today, we're going to break down the fundamental principles of how energy navigates through all these diverse systems, step by zooming in on the specific nodes that govern literally everything.
To really grasp this, I want you to imagine a single packet of energy arriving at a critical node within a complex system. It's carrying the vital power that keeps the entire machine running, whether that machine is a massive robotics assembly line or, say, the drivetrain of an electric vehicle. But as our little packet hits this node, it faces a literal fork in the road, a routing decision. How exactly is this energy going to distribute itself to keep the machinery turning efficiently? Well, when standing at this metaphorical crossroad, the energy basically encounters one of two fundamental architectures. The system is either going to force the energy to share the same effort, or it's going to force it to share the same flow. That's it. Every complex interaction in a physical system boils down to those two distinct routing choices.
Path A, sharing the effort.
Now, what's really interesting about this is how we formally define this first path. We call it a zero junction. Think of a zero junction as a connection where all the attached components share a common effort, effectively acting as a parallel system. In the world of bond graphs, this is the ultimate equalizer. Every single component connected to a zero junction experiences the exact same foundational effort. To put that into perspective with something you probably already know, think about a parallel electrical circuit, right? Every branch in that parallel circuit shares the exact same voltage, and that voltage is the effort. Or, if we look at a mechanical fluid system, imagine multiple pipes branching off from one single main tank. All of those connected pipes share the exact same fluid pressure. The effort remains totally constant across the board, which allows multiple parts to operate simultaneously under the very same driving force.
Let's move to Path B, sharing the flow, and see how this builds on what we just learned.
So, if Path A was all about sharing the effort, Path B acts as its complementary dual. It's the rule of opposites here. Enter the one junction. This is a connection where components share a common flow, which means the system is acting in series. Instead of every component feeling the same effort like we saw in the zero junction, here everyone experiences the exact same movement, the same current, the exact same flow of energy passing through them one by one. In the series framework, the flow rate is the constant, while the efforts actually add up. It's like fluid passing consecutively through a single pipeline that has varying diameters, or electrical current passing through a series of resistors. The energy doesn't split into different lanes here. No, it marches continuously through every single component in a single, unyielding line.
And this brilliantly illustrates the dichotomy, making it incredibly clear. On the one side, the zero junction, parallel, common effort. On the other, the one junction, series, common flow. Toggling between these two junctions allows engineers to map out almost any multi-domain physical system you can imagine. It is a beautifully simplified method. Because look, power is always just effort multiplied by flow, right? So these junctions simply dictate how that power is distributed without generating or dissipating it themselves. You really don't need to get lost in pages of complex differential equations right off the bat if you can just remember this basic underlying split. When you're looking at a subsystem, just ask yourself, are the parts sharing the effort or are they sharing the flow?
Section 3, the Holiday Lights Challenge.
Okay, let's put this to the test with a quick mental exercise using a classic engineering headache. We've all faced this dreaded scenario with holiday lights, for sure. You plug the string into the wall, and because one single bulb is broken or loose somewhere in there, the entire string goes dark. The whole system fails because of one tiny node. So here is the challenge I want you to evaluate right now based on how the electrical current is behaving. Is that string of lights operating as a zero junction or a one junction? Are these interconnected lights sharing a common effort, or are they sharing a common flow? Think about it for a second. Lock in your answer.
And the answer is a one junction. Yep, common flow. Because a single broken bulb stops everything in its tracks, we know for sure that the current was a shared, common flow in a series system. The energy was required to move continuously through each bulb, one right after the other. When one broke, the flow was completely, physically interrupted for everyone. Now, what's really fascinating is how modern engineering actually solves this. Today's light manufacturers often bypass this one-junction limitation by installing these tiny little shunts inside the bulbs. When the filament breaks, the shunt melts and bridges the gap, allowing the current to bypass the broken element. So they essentially turn a pure one-junction series into a more complex network. Also, the rest of your tree stays brightly lit. Pretty clever, right?
Section 4. Mastering Structural Logic.
So, the crucial point is this. When we boil it all down, these are your structural logic fundamentals. First, energy distribution always requires routing decisions based on the architecture of the system. It's like a giant puzzle. Second, zero junctions handle your parallel systems by utilizing a common effort. And third, one junctions handle your series systems by relying on a common flow. Recognizing these simple fundamentals allows for the seamless integration of mechanical, hydraulic, and electrical systems into one single, cohesive, mathematical model. You no longer have to look at a car engine and treat the electrical wiring as entirely separate from the fluid dynamics. They speak the same language. Once you know how to track the zero and one junctions, you can read the structure of any bond graph and fundamentally predict the behavior of highly complex environments.
Which brings me to a final thought I want to leave you with. Look around your room right now. Seriously, take a look. Think about the appliances, the lighting overhead, maybe the laptop charging on your desk. How is the energy in your own space structurally routed? Are the devices in your house sharing the effort, or are they sharing the flow? Once you start seeing the physical world through this elegant lens of zero junctions and one junctions, you realize that the structural logic of engineering is literally everywhere. Thank you so much for joining me for this explainer, and hey, keep analyzing those systems.